Hello. Ooh, recording has started. If anybody needs the restrooms are almost to the elevators, I think to your left or your right, like right next to the elevators. If it's an elevator, it's not a restroom. If it's a restroom, then it's a restroom. Yeah, whichever one, just don't use the elevators as your restroom. We would like to be invited back, so yeah. All right. Good. Yes.
Hello? Is this on?
Yes, it is on.
Okay.
Yes.
Okay. Hello?
I don't know. Yes. Yes.
It's quiet.
It's quiet, yeah. Go ahead.
Okay. Welcome to another Papers We Love. Can you raise your hand if you went to Papers We Love Conf last week? Yay! That's amazing.
Awesome, yes.
Thank you. Thank you for coming. That was our first one. It was great. It went really well. It was right next to Strangeloop, which was really awesome for those who went to Strangeloop. If you missed the talks, fear not. They'll be online soon.
Like next week.
Yeah. We're on it.
Yes.
If you have any questions about that conference, please let us know. Yeah, it was great. And it's amazing that we were able to do that within like 2 years of starting a meetup.
Yes,
so.
And we're all really tired right now.
We're super tired.
Yes, but it was very, very nice. We have the talks up with transcriptions as well, so that would be very good. And then, yes, if you like this meetup, we recommend that you check out the videos because they're very legit. So this is September. We are now looking for speakers and mini speakers for next year. So if you have been a regular, I'll probably remember your face and I will start asking you or volunteering you to speak. If you want to speak, just let me know and we'll start signing you up. But let's get started. So normally if it's the first time you come here, we have a short talk and we call that a mini, and then we have a feature, a full-length talk, and I tend to introduce the two speakers while telling you things that are true about themselves and also making up a lie about them. So yes. So I'm going to introduce Amanda, and she's our mini speaker. Amanda is a site reliability engineer at Heroku, and she has worked with complex distributed systems for most of her career. She currently specializes in database reliability and previously worked as a QA engineer, exposing her to a myriad of interesting ways in which technical systems can fail. When she was a child, Amanda used to have a pet raccoon called Lucky. So let's give it up for Amanda.
Super duper. Aw, Lucky. Yeah. One-handed password unlock. So thank you for coming out tonight, and thank you, Inez, for hosting and for that lovely introduction. As mentioned, my name is Amanda Gilmore, and I work on complex distributed systems. So this paper is particularly fascinating to me because it's very applicable to what I do every day. What's also really fascinating about this paper, in my opinion, is how many different domains that it touches. The paper was written in 1998 by a medical doctor called Richard Cook. And he was specifically talking about medical systems, observing ways that medical systems will fail, because medical care is also a very complicated system. But what's really engaging about this paper, and one of the reasons why it is fairly popular, chatting with a lot of y'all before the talk, I got the impression a lot of us had, in fact, read it before. It's a shorter paper, about 5 pages, so pretty accessible. And unlike a lot of the papers that we go over here at Papers We Love, this one is organized in a set of bullet points. I believe it's 15 points that go over some true statements that Dr. Cook has observed about complex systems over time. So it doesn't have as much mathematical representation of the concepts that he's describing. Now, as mentioned, I defend a complex system against failure. So a lot of the reasons why this particular paper is important hit me. And it sounds like a lot of all y'all are also software engineers and also work with complex distributed systems. So one of the things I'm going to go over as I present this paper, actually, I hate to ask this, but can I ask how many people have in fact read the paper? Okay, about half and half. Cool. Okay, so as y'all probably know, it's organized by several bullet points, and some of those are a little more thematically related than others. So what I'm going to do is I'm going to go over some of the major concepts of the paper and present some real-world examples that illustrate those concepts. Let's begin. One of the big truisms that Dr. Cook observes is that complex systems are inherently dangerous, which is kind of fascinating, right? Like we're human beings are fascinated by the things that can pose risk, challenges. We're intelligent creatures who like to solve hard problems, and danger really is an interesting problem. How do we mitigate danger? How do we keep ourselves safe? These are some of the important takeaways that we can get from complex system failure and understanding it better. Because complex systems are inherently dangerous, we've gotten really good at defending them, right, which is important and reassuring. So some of the examples that Dr. Cook himself specifically cites as an example of a complex system is power generation. Later on, I'll talk a little bit about the 3 Mile Island disaster, which is a textbook complex system failure. Also really dangerous. Nuclear energy radiation is no joke. Also, the New York blackout of the Northeast in 2003. Another classic complex system failure. Even though we have all these heavy defenses against them, necessarily, these failures still happen. So this paper looks at the ways that the defenses work. And one of those ways is that we get resiliency out of these systems. I'm going to give 2 examples here. One is a complex system that is resilient, and one that does not fit the criteria of a complex system. So how many of y'all take BART on a daily basis? Probably everybody, right? Yeah, exactly. So a great example of a complex distributed system would be a traffic network, where it can run in degraded mode. Because if there's a component failure in part of the complex system, the service is disrupted, but it's not catastrophic. Like we can listen to a traffic report to understand that there's an accident on the 101, and traffic is going to be cruddy, but like you can still get to work. It just might take you some time. And that's what Dr. Cook would characterize as degraded service. Similarly, BART can have degraded service, but to a lesser extent. It's not as complicated. It's a little more like we have fewer lines. So simplicity makes it less of a complex system. So for true catastrophe to happen, going back to like the 101, for true catastrophe to happen, you need multiple failures. This is a really important point about complex distributed systems as opposed to any other kind of system, is that you need multiple points of failures for a true catastrophe. Let's go on to that. I'm going to actually pull out a really key quote here from the paper, which is that the changing mixtures of failure latent within systems. So going back to our example of traffic, if there's an accident that causes degraded service, it's still running, right? Like our complex system is still able to operate. So for actual catastrophe to happen, you need to have multiple points of failure. So you would need a bridge. I think a good example of this would be if an earthquake happened, then you have a bridge outage, which happened, I think, in 1986. I wasn't living in the Bay Area then. But when you have a bridge outage, in addition to other road destruction happening, that's what causes the actual failure of a traffic network. Seems really grim, right? I hate to be grim, but it's going to get a little more grim. Part of the important things that we learn from this paper is that an actual root cause analysis is pointless because you need multiple failures for an actual catastrophe to occur. Now, again, this seems grim, but part of the reason that this paper in particular is so compelling is that because we're learning lessons about how the systems fail, we can improve our defenses of the systems, and we can better understand how we as human operators relate to the system. So like, what does it mean for us as human operators? The big takeaway is that we're part of the system. It's we're human operators are part of the system. So another quote that Dr. Cook points out is that every action that we take is a gamble because we can have an imperfect understanding of what's going on in each component at any given time. What we do, we don't know if it's going to cause a component that'll fail in another part of the system. I have a question. We're grokking a system. How do we? Does this help you? I'm kind of curious to get a sense from the audience. Do you like this idea of grokking a system? So this is a system that has historically not been grokked. I alluded to earlier, 3 Mile Island. This is another textbook classic system failure that is complicated. Does anybody have any, has anybody studied nuclear reactors or have a sense of how wet type nuclear reactors work now? Awesome, cool, okay, cool. So this one is actually literally close to home for me. It's about 45 minutes from where I grew up, so I have, I had a sense about how this works. So this is 3 Mile Island, and in I believe it's 79, what happened was there was a meltdown in one of the reactors. This is actually going back to what Dr. Cook describes as inherently dangerous systems. Power generation is one of the things that he explicitly calls out as being a complex system that is affected by these truisms. So what happened is a valve failed, right? Like a single valve failed. Now, that seems to go counter to the idea that root cause analysis is pointless. However, that single valve failure on its own wasn't enough to cause true catastrophe. What then happened is another part of this complex system, the water pump, detected, so the sensors that detected the temperature in the reactor realized, oh, hey, this is too hot, we need to cool this down. So these water pumps start pumping in water to the reactor to cool things down, which is what it should have done, right? Like, that's not a component that's failing, it's a component that's doing what it's supposed to do. Here's where it gets interesting, is that the people who operate the reactor, so the engineers working for the reactor, hear the pumps going too quickly and realize, hey, something's not right here, we need to fix this. So what they do is they turn off the pumps, and that is what causes this meltdown, is that they didn't know, because what happened is our information was faulty with I used the we in the sense of like humanity's information was off here because the sensor that indicated to the people that the valve was closed was wrong. So you cause a couple of different failures, right? You cause a failure of the monitor, or what caused the catastrophe is several failures in concert. You have both the valve failing, you have the monitoring to let us know about the valve failing, and then the human decision to turn off the pumps. So it's important to realize that we're part of this integrated complex system. And again, this seems grim, but this is where the paper itself becomes really powerful, is that even though we can never have a full understanding, we can never fully grok the complex system, we can learn things after this catastrophe and improve our own interaction with it and improve those defenses, because it's, again, heavily defended against failure. How can we improve those defenses? How can we learn from those failures and use this paper to understand, or rather to organize our learnings? So what was the upshot of 3 Mile Island? This is really exciting, is that now there are accreditations for nuclear operators. There's a rigorous certification process that you now go through. And again, going back to me as a complex system operator, is going through methodically, having a checklist to understand how to manage that complexity is how we as humans can fully wrap our heads around the complexity of a system like this. So even though 3 Mile Island is, it was a disaster, but we still can learn from it, and we can use the ideas in this paper to organize those learnings to make better and safer complex systems. So thanks for listening. I'd love to take any questions if y'all have some. Oh, we have another mic. Yay.
Yeah, I appreciate you bringing up the point about root cause analysis from one aspect and another.
Yeah.
You know, it seems, I'm going to give the contrarian view because I'm interested to explore this a little bit more.
Yeah, please.
Because, you know, if we don't look at what, even if it was the valve problem, at the root cause being the earthquake, or some root cause, if we don't examine what the input to that system was that caused this catastrophic failure, would it be an improper posit to say that then we wouldn't know ways of better guarding that system? So in some sense, we do have to dig to the root of finding why this failure was able to take place.
That's an excellent question. I think the distinction here is less about retrospecting. On the contrary, I think retrospecting is the most powerful tool that we as human beings have, that we can analytically look at things in a detached way. Rather, what Dr. Cook is talking about is that there's no one single point that causes the failure. So there is, as you say, like that's a great example that there is an originating point. Actually, a friend of mine, when I was talking about this paper, mentioned the fact that in the 2003 blackout, that was traced to a big branch falling on a transformer in Ohio, which killed the Northeast. At least its power grid. I was living in New Jersey at the time. We had brownouts, but like it wasn't complete failure like the New York City metro area experienced. So yes, you're right in that there's so much value in retrospecting on that, but rather what Dr. Cook is talking about is the fact that there isn't any, like the tree branch is what caused the cascade of events. However, because it's a complex system and there are other components that also failed in concert with that tree branch, that's what ultimately resulted in the entire Northeast being out of power. Yeah, does that help? Right? Right? I know. I'm sorry if I seem really weird or grim being excited about disasters like this, but it's really fascinating to know how we can defend against it. Go for it.
So are there any comments by Dr. Cook on the biological metaphors, like the way biology handles failures, degeneracy and redundancy?
That's an excellent question, and since I haven't seen his talks in person, I think Inez actually looks very excited. Would you like to answer this? I know you've seen Dr. Cook speak recently.
Make sure that the microphone.
I'm not usually accused of not speaking loud enough.
That's an excellent point, and I unfortunately cannot speak to what Dr. Cook himself has said on the matter since I haven't seen him speak in person, but that's an excellent point. Bit of personal information. I don't have a gallbladder, right? Like, I had to have my gallbladder removed in 2009. I'm still a living, breathing human being. I'm running in degraded mode, so that's a good example.
Thank you. Thank you.
You're welcome. Yeah.
I do have another question, and it's a little out of bounds for your presentation. It's totally fine if you want to decline to answer it, because it deals with the paper, but you didn't address it in your talk, per se.
Okay.
No.
Because I invited that one.
What it was about was, he talks about the idea that we are both producers of the systems, of both failures and of the product of the system itself.
Yeah.
So I was wondering if you had any comment about that, if there was any additional information or light you wanted to shed on that particular aspect of the paper.
I'm very glad you mentioned that, because that is in fact something that he mentions, is the fact that humans we're just as likely to cause failure as success. And that's a big part of where his bullet point that every action a user takes on the system is a gamble. And that's part of it, because often those gambles are successful. And the fact that there's always that latent failure potentially hiding behind the surface, I almost think of it sort of like, you know how like whenever you take high school physics and they talk about like kinetic and potential energy and like actual energy, it's like there's this potential energy of disaster hiding in a complex system. And even if we take a gamble that's successful, that potential is still there. We just haven't realized the potential. Does that help answer? Yeah.
Also, at some point, he has a talk and talks about systems and us as like producers of systems and exposing configurations as something that people are going to use and abuse in ways that we're not understanding. Mm-hmm. So the fact of how you expose the interfaces to like, or how you actually let people operate your system is also something that would be like a vector for either catastrophe or not, and then that you should be aware of, like how you expose those configurations, because they're just going to be used in ways that you don't understand. But he has another talk about that one, and that one is really good too.
I had a comment as opposed to a question. I wanted to say thanks for your expansion on the topic, because when I came here, I didn't know if it was just going to be a coverage of the bullet points, but I appreciate you going into other areas and bringing additional examples to it. So.
Thank you. I appreciate that.
One more question, you?
Yeah, I guess this is another request for further commentary. I might have misread the paper, but one of the points was about something like if the system is too stable for a while, like if it's operating without a lot of failure, then it's more likely to tempt people to make change that will cause failure. It seemed like a very pessimistic outlook of all systems. Do you have any comments on that?
I do. I do. I think this goes back to regarding humans as part of the system, effectively, because like with the 3 Mile Island incident, for example, like the humans operating on the system in concert, like the system does a thing and then we do a thing, but the thing is the wrong thing. Yeah, so the paper itself looks more at like the truisms of complex systems rather than human nature. So if I'm strictly speaking to canon, it doesn't address that. But I do.
Yeah, I think it seemed to imply that it was a danger. It wasn't an inevitability, right, that people would change the system because it was too stable, but that it was like a danger of a stable system.
Oh, I see what you're saying. Yeah, I think that would best be articulated like with the Valve case and the fact that the inputs that people were receiving were incorrect. And one of the takeaways that we, as complex system operators, need to understand, and this is something I do in my job all the time, is I'm questioning, are my inputs accurate? Like, are the things that my system is telling me, is this even accurate? And how can I check that assumption? So, speaking anecdotally, that's a good point. I don't think humans are necessarily good at that. That's like a habit we have to acquire. But that's the power of this paper, is that it can reveal for us the dangers of those complex systems so that we can be more aware of that and learn to check those assumptions. Does that help?
Yeah.
Okay, great, cool.
Okay, so we're gonna do a 2-minute break while Tony sets up. If you need a restroom, you know where they are. If you want a little bit more of beverages or more food, it's there. 2 minutes. So, woo. Thank you, Amanda. Also, if you need chairs, there's chairs in the front, so there's still like room, so you don't have to stand up. Elevators are not restrooms. Yes.
Are you Excellent. Well, let me get out of your way. Good job. That was great. Yeah. Thank you.
We have like points.
There we go. I mean this in like the nicest way. I thought the length of the talk was really good. Awesome. Oh, great. I worked on that, so I'm glad. Yeah. Oh.
We've had minis that were like.
I don't know what's wrong with this mic, but apparently it's very quiet. I really try to do that, but I'm not sure if that the volume mic is recorded. That's my.
Okay. No, I'll just.
Yeah, exactly. I know.
I'll just use whichever. I was just curious.
It's a little louder, but it sounds like there's probably like a board and it needs to like be like volumed up. No?
Hello?
This one?
Too.
Yeah, that should work.
That should work.
All right.
There's the power over here if you need.
It sounds really loud.
Yeah. Don't kill us.
Yeah. Do you want the loud one or the quiet one? You can take the loud one. I'll take the quiet one.
No, let's leave the loud one for him.
Do you want the loud one for you? Is this working?
Sure, it is not.
No, so let's get the
I'll take
okay.
that one, whatever.
Take the loud one because he has like, yes.
Cool. All right.
This is on.
It's on. Okay.
It's on. Wait, that?
All right. Yeah. Cool.
Hello. Okay. All right. I think you have something that you wanted to say.
Yeah. A note from our sponsors. Thank you to Wikia, thank you to GitHub, and thank you to Fastly for helping us make this happen every month. And if you want to sponsor or contribute, we are welcome to those contributions.
Yeah.
And then next month, we're meeting on the 13th at GitHub. Brian Fink is speaking.
That guy
That
over
guy.
there. Yes.
Sorry I waved to you.
Woo. Okay, one second. All right, so now we're going to introduce Tony. Tony's a cybersecurity engineer at Square. He cyber tweets about cybercrypto and cyberprivacy. Cyberinventor of celluloidrb and the cryptosphere. In his spare time, Tony plays in a Depeche Mode cover band. Let's give it up.
That may not be too far off. All right, hi everybody. Thank you for coming. As Ines said, I'm Tony Arcieri, and this is a protocol for interledger payments. So this is a talk about payment networks, and more specifically, modern payment networks that operate over the open internet. So I'm going to start out by talking about this guy. This is Paul Baran. Just curious, anybody know who he is? One person, wow. So this guy basically invented the internet. So in 1964, he published this paper called On Distributed Communications Networks. And there are these three graphs in this paper, which somehow seem to hit my Twitter feed like every day. People have kind of adopted these and tried to use them to explain some emerging ideas in things like blockchains and that sort of thing. So we get these three basic, so these are network topologies, right? Nowadays, we would probably call these a star, a hub and spoke, and a mesh network. Actually, Paul Baran uses that terminology in the paper. But he's trying to contrast these three different networks, right? So centralized is easy to understand. Decentralized is a little more interesting. So he only spends about 2 sentences or so describing this in the paper, and he throws scare quotes on it, and it says, like, some people describe it this way. So it's almost like he's trying to distance himself from this concept, right? As if people are misapplying the name decentralized and using it to describe something which is, in fact, a little bit centralized in a way, right? So really his point in this paper is we don't want either of these two topologies. What we really want is this distributed network. And he goes on to show something a little more like this, right? So we have heterogeneous transports that are all speaking the same network protocol and are all interconnected. And basically the point of the paper is if any node in the network is connected to at least 3 things, the network is highly resilient. So I thank Amanda for opening the talk, because it kind of goes to my point as well, right? How do we build these big complex systems that are in fact resilient? So this is one of the ways we do it. It's lots of redundancy. So this is a quote from Nicholas Negroponte from his book in the early 90s, Being Digital. And he was trying to get the same idea across, right? If we build more interconnected systems by their very nature, they're just more resilient. So people have been kind of appropriating these graphs and pasting them into various slide decks, as I mentioned earlier. And they've been trying to attribute this idea of decentralization to things like Bitcoin and Ethereum. And at the same time, we have centralized SQL, even though, people are building pretty cool distributed SQL databases. Here's another one of these. This one is particularly funny to me because they're trying to apply it to land titles. Last time I checked, my title company is a network, and if it is, their packets are paper. Here's another one. So I think what people are doing is colluding the actual network topology with the trust model. So these are some graphs that try to combine them into one, and I don't really think that's helpful, right? I'm mainly concerned about the network topology and less so about the trust model. So I just can't make sense of these graphs. So I'd like to make a bit of an audacious statement here and say that actually Bitcoin and Ethereum are somewhat more of a centralized system. And if that's the case, what do these other two actually look like? So I'm going to start out by talking about these centralized systems, starting with systems like Bitcoin and Ethereum. I'm going to argue the central point is the blockchain. So I say Bitcoin is centralized. What I mean by that? So it's running on a peer-to-peer network. Clearly, the peer-to-peer network is decentralized. But when it comes to being an actual payment network, the way we actually send money through Bitcoin is through the winning miner. So Bitcoin's capacity is fundamentally limited by how many transactions the winning miner in this every sort of 10 minutes lottery is able to put into a single block. So this isn't a value judgment on Bitcoin. Blockchains are shared ledgers, and shared ledgers have benefits. It solves the reconciliation problem, and that's pretty valuable. But in Bitcoin's case, there's kind of a problem. Bitcoin can only push 1 megabyte about every 10 minutes, which is slightly slower than a 14.4 modem. And the entire system has been approaching the capacity of the network. It'll get there relatively soon. They're trying to ship a sort of stopgap that will raise the capacity a little bit, but if it ever gets there, the system will become highly congested and unable to perform transactions. So the question is, can we move some of these transactions off of the Bitcoin blockchain so it has more overall capacity? And we get to a decentralized system here. I'm using this term a bit liberally, but I think it applies. So I'm going to talk about the Lightning Network, which is one of the plans to do this. And the idea here is we can add these nodes that live outside the blockchain and act as a sort of caching layer for Bitcoin. So we can offload some of the load from the blockchain, so not every single transaction has to go through it. So this has been prototyped with a thing called the Thunder Network. Here's their diagram. So I think their idea is you personally maintain a sort of like L1 and L2 cache of your wallet. Seems kind of complicated to me, but so you have two wallets, one that lives on the blockchain and one that lives on the Lightning or Thunder network, and then you're able to send payments through these independent Lightning or Thunder nodes. So here's the Lightning paper. I've tried to read this paper, and it is really, really complicated. So I think I'm kind of in their target audience of people who should be able to understand this paper, but I'm afraid I just don't understand. But I'm going to try to explain it anyway. So the core idea is this thing called payment channels. It's the idea that you can open a payment channel that's taken off the blockchain, send a transaction to another party, and that party can then put it back onto the blockchain. And we can loop in multiple third parties here in a sort of directed acyclic graph. So this is kind of similar to that graph you saw earlier with the Thunder network. And the idea is there is a time bound on which you have to get your transactions back onto the blockchain. And so you close the payment channel, and if you fail to do so, if you miss that deadline, the entire payment channel times out and nothing moves. All right, so that's great, but what does an actual distributed payment network look like? The main thing I think is important is this idea of routes. So if you're looking at something like the OSI model, it's about having a layer 3. And the core idea of routes is, given 2 points, there are multiple ways that we can get from any source to any destination. So that's the core idea of Interledger. So Interledger is work. It's being standardized through the W3C, but is primarily developed by engineers at Ripple. And the core idea is we're never going to get everybody onto a single ledger. So I think when Bitcoin originally came out, people were kind of excited about this idea that everything could just go through Bitcoin. But then Ethereum happened, and then, oh my God, there are multiple different cryptocurrencies, and then there's also all the money that everybody actually uses. So how do we build a system that connects all of these together? So that is the core idea of the Interledger paper. And specifically, to do this, we need a system that has no central point of contention. It has no blockchain, because it is trying to be the system that's connecting everything together. So this is a little bit of a snarky comparison of Lightning versus Interledger, but hopefully it gets the point across. I think Interledger is almost beautiful and Zen-like in its simplicity compared to something like the Lightning Network. There's also this idea of peg side chains for combining or for doing payments between blockchains. So I think Interledger combines the ideas of the Lightning Network, peg side chains, and can work with real banks that exist today, like legacy fiat currency and real money. And also, the other thing I really love is it's developed with formal methods. So it's very rigorous in its design, and I think it could actually work. So the core idea, kind of going back to Paul Baran, is that we can interconnect all of these different payment systems together and pick an optimal route. So in layer 3 terminology, we could do, instead of open shortest path first, we could do a open cheapest path first algorithm to find the optimal way to go from one currency to another. So the core idea in Interledger is they call it chains, not to be confused with blockchains. I called it routes here. So you can find any sequence of these connectors through the Interledger to conduct a particular payment. So this is accomplished by connectors. So you have some third party, in payments terminology, we might typically call this a clearinghouse. This can be done through things like bidirectional credit lines between two participants. But the basic idea is you have somebody with accounts on both ledgers who is able to receive funds on one and provide funds to a recipient on another. So the core trust model of Interledger is built on ledgers. So a ledger can be a bank, it could be a blockchain. So Interledger can connect them both. Ledgers are kind of the core anchor points of Interledger's trust model. So they keep track of all of the balances of all of the participants and perform these things called book transfers. A book transfer is an internal transfer within a ledger from one party to another. So connectors are how you move money between ledgers. So these are the party in Interledger that ends up assuming most of the risk. So they will have an account on each of the ledgers, and when you want to move money between them, they're who the payments flow through. And they ultimately have to trust that the ledgers are honest. If so, they're able to collect fees for performing transfers, and therefore link all these ledgers together into a global interledger. So there's this concept. It's described in the paper as escrow, but I think it's more typically called a hold. And the idea is if you want to move money between ledgers, what you do is you first say, I want to move this money from one account to another, but I'm not going to do so until I receive proof that money is moved on another ledger. So it's a way of tying up funds in such a way that they won't be released until you've received effectively a receipt from the other ledgers saying that the money is moved there. So this is the fundamental way that funds are locked and unlocked when they're moving between connectors. And then to transfer money, what we do is move the money on the destination ledger. We get a receipt from that ledger saying the money is moved, and then we can provide that receipt back to the source ledger and unlock those funds. So the trust model is probably the most interesting part of this paper. So Interledger tries to reduce the risk of any of the participants in the system and focus on the ledgers being the fundamental foundation of trust within the system. So if you have an account on a ledger, you fundamentally have to trust it. So you shouldn't put your money in a bank you don't trust. If you're a connector, you ultimately have to trust both of the ledgers you're connecting. So, I mean, this goes the same for if it's bank or if it's blockchain, right? Like if it's blockchain, you have to trust that the software actually works and will release the funds when you tell them to. If it's a bank, you're trusting they're not just fudging their numbers, that they're not stealing money from you, etc. So fundamentally, the trust is on the ledgers, and the counterparty risk, the risk of losses, is assumed by the connectors. So Interledger uses cryptography to mediate the process of connecting ledgers. And the way it does this is primarily through asymmetric cryptography, the idea of digital signatures. So what you do is you have a ledger sign that a particular transaction was performed on a given ledger, and use that as the way you unlock the money on the sender's ledger that has been escrowed. So this is actually not described in the paper. It's called Crypto Conditions, and they have an entire spec for it. The URL is there at the bottom of the page. Let's see, whoop. So there are, this is a state diagram of the states that transfers can be in. So to initiate a transfer, the first thing you do is you propose it to all of the ledgers, and then it is prepared. And after that, it will either be executed or aborted if the transaction times out. So Interledger supports two different modes. I'm going to describe universal mode first. So the second mode is called atomic mode, and it's actually the first mode they describe in the paper. And when I originally read the paper, I thought I liked atomic mode better. So atomic mode is much more complicated, and at first that made me feel safe, but the more I've thought about the problem and better understood it, I think I actually end up liking universal mode better. So universal mode both modes have this concept of a payment chain. So a payment chain is the way we have this sort of multi-hop route between different ledgers. So here we have a couple banks and Dogecoin, and between each of those ledgers is a connector. So we have Alice wanting to send a payment to Bob, going through two connectors. Each connector has an account on both of the respective ledgers they're trying to move money between. And each of these hops, each of the connectors is taking a fee. So here's a state diagram of how this actually works. I'm going to step through this with some animations if you don't want to stare at this intently. But the basic idea is there's one round trip of proposing a transaction, and that's when the holds are placed on the respective funds. And then there is this second phase of effectively capturing the money. It's kind of like auth and capture if you've ever done credit card transactions. So here's a diagram of how this works. So these payment chains can be kind of arbitrarily long. So the first thing we're going to do is propose a transaction. We're going to get all of these ledgers to issue holds for the money that's going to flow between the respective parties. And then we're going to effectively capture. So what we're going to do is have this cryptographic receipt of payment flow from the recipient's ledger to all of the parties that are connecting this particular chain. So this process kind of happens backwards, which is kind of counterintuitive maybe. But the idea is each of the connectors are effectively fronting the money until we get all the way to the original sender. So they're handling the counterparty risk effectively. So once this first transaction has happened, we're locked in at this point, and either we will get all the way to the sender actually sending the funds to the first connector, or we'll encounter a fault, and I'll talk about what happens then. But the basic idea is this receipt will continue to flow backwards until we get to the sender. At this point, all the funds are unlocked and the payment chain is completed. So what happens if there's a fault? And this is by far the most interesting thing in the paper. I'm not going to go into it in detail, but I just want to get the general idea across and show how this actually works. So let's say we have this connector that fails to deliver this receipt to the next ledger backwards in the chain. What ends up happening then is they pay the funds to the next ledger, to the next connector in the chain, and then they're never able to unlock the funds to get their payment. So in this case, at the end of the day, the connector ends up holding the buck. They are they're the ones taking on the counterparty risk here. So in this case, the original sender is never going to get the receipt. The recipient is going to wind up with the money. So this is bad, but effectively, each connector in the chain is incentivized to get that receipt back to the ledger earlier. What? Battery on it. Hello? All right. Yeah, so each connector is incentivized to deliver this receipt because if they don't, they won't get their money. And there are timeouts that are set when the chain is set up to kind of give each connector an SLA to deliver this receipt. And they're kind of additive, right? They're kind of this additive cascade. So we give each connector in the chain a little bit more time the farther back we go to get that receipt back to the connector that's earlier in the chain or back to the original sender. so that if the next connector in the chain delivers that receipt, there will still be time for that connector to deliver the receipt backwards. So it's not entirely like a two-phase commit protocol. Ultimately, I'm a security person, right? I'm on the platform security team. So kind of what the risks are here would be the ledger on the left-hand side there. So the one they're effectively trying to send the money from, right? So that could go down, right? So it could have an outage, and this connector, is kind of ends up holding the buck. So at that point, they would have a dispute with their ledger, right? But fundamentally, they're connecting these ledgers. They have to trust them. Maybe another problem would be like a denial of service attack against them, right? So somebody is trying to defraud one of the connectors, so they target them, and they get the funds to the recipient. The sender doesn't end up paying anything, and you just end up defrauding these connectors. So those are kind of the risks. So what do we do about those? So Interledger provides a second mode called atomic mode, and what this does is run a consensus protocol across all of the participants in the payment chain. And it puts the trust in something called notaries. So notaries, there are different things that could be notaries in the real world. I like to think of someone like an underwriter performing this role. So you can imagine there's somebody who's fronting the money in this case. They ultimately have an underwriter who's typically going to be a bank. And that bank actually is more incentivized to care about the money they're underwriting than the company that's actually performing these transactions, right? Like that company could go bankrupt. It's the underwriter who's ultimately going to eat the loss here. So how this works is, so it's sort of similar to universal mode, but at the very end of this, the notaries are the ones who ultimately say commit. So both participants need to agree on the notaries they're going to use, but once they do, the notaries observe the entire transaction, and if there is any sort of dispute, they can see all of the states that occurred across the entire chain and be the ultimate arbiters as far as like where did this go wrong and who should actually be responsible. So the entire protocol, both in universal mode and atomic mode, is described in terms of TLA+. So the TLA+ is the temporal logic of actions. It is effectively a programming language for writing proofs about distributed systems. It was developed by Leslie Lamport, who's kind of famous for the Paxos protocol. Their particular proofs are adapted from the Raft source code, but they have shown that using temporal logic, Interledger actually holds up. So I think that's pretty cool. And what they're going for is a OSI-like layered model. So they're trying to boil the entire problem down to its roots and build a common system that can work across all payment networks and kind of punt all of the complexity up to higher layers that will run on top of Interledger. So there are a lot of open questions here. The main one is the routing protocol. So how do you actually pick these routes? How do you pick these payment chains across the Interledger? So the main one they started with was this idea of source routing. If you're familiar with source routing, it's not very commonly used on the internet, but it's the idea that the initial sender of a packet can say the entire path across the network they want to take. So that feels very empowering, right? It's like you can pick the cheapest route that you see as an individual, but what they've been talking about especially since a lot of payment networks, even ones that are private, don't use IP necessarily, don't run over the internet, have been trying to solve the same problem and trying to find the cheapest path across disparate federated payment networks. So they're looking at ways that the ledgers can actually assist in picking optimal paths. Another important one is identity. So right now, there isn't identity as part of the core protocol. So you, as somebody using Interledger, if you're a connector, if you're a ledger, they don't necessarily see who you are. So that's cool from a privacy perspective. Where it actually kind of falls down are these regional laws. So there are these two laws called anti-money laundering and know your customer within the United States. So the idea of these laws is we don't want to give money to terrorists and things like that. So we want to know who people are who hold bank accounts and who they're giving their money to. So this is kind of punted to we will need protocols and mechanisms on higher layers of this protocol that are able to accommodate these laws. And finally, dispute resolution. So I mentioned, what happens when you're doing one of these universal mode payment chains and it fails. How does somebody go to their ledger and go, you were down, I was up, I was trying to complete this payment chain, and then your ledger went down, the money moved, and, you owe me some money because you had an outage. So these are all open problems that can hopefully be solved by higher level mechanisms on top of Interledger. Why I'm not too particularly concerned about this is I like the way they're, handling the layering here. I like that they want to have a core protocol that is agnostic of all of these problems, that can work across systems and fundamentally only solves the core problems, so that systems built on top of Interledger can, solve more of this region-specific errata. So ILP is Interledger protocol, and it's not a science experiment. It's actually about to go live. So Ripple is shipping this to some of their customers, and they're about to start moving real money with it in a little less than 2 weeks. So it's a real protocol being standardized through the W3C, and yeah, it's going to start moving real money soon. And that's it.
All right, so we're back. Questions? All right, I'm going to start. Ryan.
So I just skimmed, but the thing that caught my eye in the paper was that there's a timeout central to this protocol.
Yes, timeouts are very important. Several of the sections deal specifically with how they pay. So there's not one timeout is right. A very fundamental concept, I think. So there are multiple timeouts throughout the chain, and they're different.
Right.
And so understanding how the timeouts work is very core to understanding the paper, I think.
Completely agreed, because they say, what they call it, a connector should choose a timeout based on their risk, and they should charge a fee based on the risk of the timeout that they're willing to, tolerate. But I didn't see anything that gave an idea of how you should actually value this, trade-off. And if they're going live, do they say something about that?
So I haven't seen something specifically of how you weigh risk versus reward for picking the timeouts, but they do definitely include algorithms for picking optimal timeouts across a payment chain. Fundamentally the core idea, almost the aha moment in this paper, is in universal mode how you pick those timeouts so they're sort of cumulative and they give enough time such that, after the money starts to move, after that first connector receives the initial receipt, and provides it. So you're that point where you're locked in, right? It's how you provide enough time for the remaining connectors to always, not always, but in the optimal case, right, get that receipt all the way back to the sender. So beyond that, sort of like you need this cascade of timeouts that vary from connector to connector, and you add a little more time each hop you go backwards. It's kind of like you're increasing the TTL almost.
Right.
Beyond that, they have an entire section in the paper on it. I don't completely understand it.
Then there are people that would say there is no good timeout to choose.
Yeah, so I mean, it's a trade-off in convenience for the sender. So you want the entire chain to complete quickly or fail quickly, right? It's kind of like we have the EMV problem of we just moved all these chip cards, and now people are very frustrated because they're slow. So you want to set the timeouts as small as you can for the user experience reasons, right? So you want the system to be convenient, but at the same time, you need to leave them big enough that real world conditions will allow the payment chain to complete and not time out.
My understanding is relevant to what you guys are talking about. The one thing that you highlighted about atomic mode was a different sort of risk. Distribution of risk, but there's also a different distribution of speed. Atomic mode can make the whole thing happen faster. So if you assume that connectors are going to price in the faster the timeouts are, the better it is for everybody involved in the payment up to the recipient, because their money is put on hold for some amount of time. So making the whole transaction faster can also make it cheaper.
Hello. I'm curious, so for each ledger that's connecting in the chain, much like an actual financial institution needs to have so much cash on hand in order to do business, does the paper quantify how much, let's say, how much padding or wiggle room each ledger needs to have on hand in order to handle the escrow transaction? Is that quantified or calculated in the paper in any way?
So no, it's not. They kind of punt on all of those. So the idea is what they're performing is something called a book transfer. So the transfers that are actually happening between these ledgers don't necessarily correlate to any sort of transfer in the real world, right? So there are different ways you can imagine this being set up. So one is a connector is something more like a traditional clearinghouse. So a clearinghouse doesn't necessarily have any direct relation. They don't own the accounts, right? They're only mediating the transfers between them. So that's one way you could set this up in the real world. Another way is you could have these bidirectional credit lines where each party issues the other party so much credit, and then they can pay that off at whatever interval they want. So you can imagine they would settle nightly, but perhaps not, right? Maybe there's some day where a whole bunch of money moves and one of the ledgers doesn't actually have the money on the books to settle nightly, right? So perhaps if something like that happened, the other party in this relationship would effectively provide a loan and they could pay that off or something like that, right? So there are different ways in the real world you could structure this as to whether or not they're a good idea. Well, that's why you have underwriters, right? So you'd ultimately have somebody holding the purse at the end of the day who's responsible for if a whole bunch of money moves and the other ledger can't actually pony up in the real world.
So brick and mortar banks simply use compensating transactions when they settle up to handle these cases of the lost receipt, say. So when the guy who was down comes back up, they say, oops, let's do a compensating transaction and make everybody whole. Why isn't that part of the protocol?
So I think what's nice about the way it's structured is a lot of these things can happen out of band of the protocol. So before you would even do any of these things, right, you would have a lot of like legal setup in the real world. So you would, in the United States, for example, you would probably need a money transmitter license in every single state you want to operate in. So, you know, like, as I said, there are all sorts of like regional errata depending on where you're operating. So to even participate in this network, I think, you know, you're going to have to do a lot of homework. You're going to have to find an underwriter. And really the idea is a lot of this, you know, a lot of the messy financial stuff can happen out of band of the actual protocol. And they want the protocol to kind of gloss over that and just work.
So a couple of questions. One, can you shed some more light on this cryptographic receipt that gets passed around? Like, is it a signature? And if so, like, what are they signing? And then a follow-up there is, if a connector trusts both ledgers on each side, why have a cryptographic receipt at all?
All right, yeah, both good questions. So crypto conditions is actually kind of complicated. So it's almost like a smart contract language, but not quite. So it's more like an authorization language almost. So you have effectively credentials, for lack of a better term. They can take the form of signed messages by a particular public key. They could be a pre-image of a hash. They could be a prefix of a hash. So there are different ways you can have these various credentials, and then they provide a sort of like Boolean algebra you can use to link them together. So, for example, you may need multiple signatures from multiple parties. So you might need a signature from the notary and a signature from the ledger, or multiple notaries even, or a quorum of notaries to unlock the funds. So then you asked if you trust both the ledgers, why you need the receipt, and the reason is because it's a payment chain. So so to give the receipt to unlock the funds to things earlier in the payment chain, when you're getting back to the original sender, you actually need these signatures from all of the ledgers in the chain. So even though an individual connector is only trusting the two ledgers that they connect, in terms of the entire payment chain, you need to collect all of these signatures the entire way. So I kind of glossed over that when I showed the one receipt moving. The receipt probably should have been growing and getting longer the farther back it goes in the chain. So ultimately, the cryptography allows you to provide a sort of irrefutable, linkable trace that all of the ledgers actually agreed to release the funds, even though they weren't running the consensus protocol in universal mode.
Questions? No more? Awesome. Thank you, Tony. All right, so we'll see you next month. If you have things laying around, the trash cans are behind. So thank you so much for coming.
Oh, hey, nice man. Yeah, for sure. Yeah, and I am working with the Baron Graph. Oh, yeah? Yes. We're using it as a model of a data center that's been rotting in place for a while. Yeah, nice. So it's nice. I don't think we've done things to